Concurrency in Rust gives you both performance and safety at the same time. If you've worked with concurrency in other languages, you know how easy it is to run into issues like race conditions, data corruption, or unexpected crashes. Rust prevents a huge chunk of those problems at compile time, which is just amazing. Now, let's start at the beginning. When we talk about concurrency, we're usually talking about running multiple tasks at the same time. In Rust, the simplest way to do that is with threads. And luckily, Rust makes spinning up threads really easy. Here's our first example. Okay, what's happening here? We call thread, spawn, pass it a closure, and inside that closure we loop and print out some messages. Meanwhile, the main thread also runs its own loop. So both loops interleave their outputs. Now, a small catch. If the main thread exits before the spawned thread finishes, the spawned thread will be killed prematurely. You'll see this if you run the code. You might not always get all 7 messages from the spawned thread. How do we fix that? We use join handles. Let's try it. Now, after the main thread finishes its loop, it waits for the spawned thread to complete with handle.join. And unwrap is there to handle errors if the thread panics. Okay, so far so good. But what if we need threads to share data? That's where things get tricky. Let's say we want multiple threads to update the same vector. If we try something like this code won't even compile. Why? Because the closure passed to thread. Spawn might outlive the main thread's scope, and Rust won't allow moving a non-static reference across threads. Plus, even if it did compile, mutating the same vector from 2 threads could cause undefined behavior in other languages. Rust protects us here. So what's the solution? We use Arc, atomic reference counting, and Mutex. Arc lets multiple threads share ownership of a value, and Mutex ensures that only one thread accesses the value at a time. Here's how it works. So let's break that down. We wrap our vector inside Mutex for safe mutation. Then we wrap that Mutex in an arc, so multiple threads can share ownership. Each thread clones the arc, locks the Mutex, pushes its value, and then the lock is automatically released when the variable goes out of scope. At the end, we print the final vector, which now contains all the values pushed by the threads. This is one of the most common concurrency patterns in Rust, Arc plus Mutex. But now comes the deeper question. How does Rust even decide what is safe to send across threads? That's where the send and sync traits come into play. Send means ownership of the type can be transferred safely to another thread. Sync means it's safe for multiple threads to reference the type at the same time. For example, most primitive types like i32, bool, or string implement both send and sync. That means you can pass them across threads or share references safely. But something like RC, reference counting, does not implement send or sync because it's not thread-safe. That's why we have Arc instead, which is an atomic, thread-safe version of reference counting. Let's actually demonstrate this. If I try to use an RC across threads, this won't compile. The compiler will yell at you that RC cannot be sent between threads safely. And that's exactly the point. Rust stops us before we do something dangerous. If we switch RC to Arc, everything compiles fine. So the summary is, threads let us run tasks concurrently. Arc plus Mutex give us safe shared mutable state. Send and sync traits are automatically implemented by the compiler to enforce memory safety across threads. Rust's concurrency model is designed to make data races impossible at compile time. It forces you to be explicit about how you share data between threads, and once it compiles, you can be confident that your program won't run into undefined behavior.